It's my pleasure to introduce the moderator for today's session, ASCE Texas Section Vice President for Technical Affairs, Bob Stevens.
Thank you, Mike, and thank you all for joining us for today's Texas Section webinar titled Trinity Railway Express, Crossing the Trinity River. I'd like to thank the branches for hosting sites, and as the State Association for Civil Engineers, we're happy to provide this service to the engineering community. If you're not a member of ASCE or the Texas section, I invite you to become one so that you can benefit from becoming a part of this professional association that has over 150,000 members around the world. Now I'm pleased to be able to introduce our presenter for today's training, Fadi Faraj. Fadi is a licensed professional engineer in the state of Texas with more than 20 years of experience. He holds a Master's of Science in Civil Engineering from the University of Texas at Austin, extensive experience in geotechnical engineering and construction materials testing for infrastructure projects. Most of his experience is in Texas, providing him a vast knowledge of Texas subsurface, stratigraphy, and local design and construction practice. His technical skills are complemented with his managerial and leadership skills. He is a graduate of both the management and leadership programs of the Institute for Generative Leadership. In 2016, he became the Vice President of Operations for the first HVJ Associates franchise in North Texas. He's been a member of ASCE since 2002, and he started his journey by serving as the chair with the Houston branch on the hospitality and primary and secondary education committees. He serves as chair of the Texas section Geo-Institute. And now, Fadi, we're ready for your presentation.
Thank you, Bob. And thank you everyone who's attending today. Our presentation is about the Trinity Railway Express crossing the Trinity River. We're going to talk about geotechnical design and construction challenges on this project. So here's the outline of the presentation. We'll start with the introduction to HVJ, and then the project background, the geotechnical investigation we did, and the design of foundations, design of T-walls, and then the construction of large offshore shafts we use on the project, and also the construction of the T-walls. So at HVJ, we practice geotechnical engineering, also construction materials engineering and testing. We do pavement and civil design, and also we do environmental geology / engineering. These are some of the markets that HVJ works in: roads, water, wastewater, flood control projects, airports and ports, rail and transit, building and parks. Here are some pictures of some of the projects. On the top right is the Port of Houston. On the bottom left this is the Shoal Creek landslide we had in Austin. And at the bottom right is the DFW Connector project we're wrapping up now. So a little bit of history about HVJ. It was established in 1985 by Herb Johnson. And then in 2016, it became the first engineering franchise in the United States. We have a Dallas franchise and an Austin franchise. And we have offices across Texas. Overall, we have more than 150 employees system-wide, and we're always looking to recruit new talents. I'm with the HVJ North Texas franchise. So we're a local North Texas firm. We're HUB certified by the state. We're also DBE, MBE, SBE certified by NCTRCA. Our labs are accredited by AASHTO for concrete, aggregates, soils, and asphalt. And our equipment is maintained in laboratories that are climate controlled. And also we follow ISO requirements. These are some of our clients. We do transportation projects for NTTA and TxDOT. We do mass transit and rail projects for DART and Trinity Metro, which today's topic, the TRE is operated by DART and Trinity Metro. Also, we do aviation like Dallas Fort Worth and Dallas Love Field. We do water projects like NTMWD, Regional Water District, the Upper Trinity Regional Water District. TRWD also, educational institutions like universities like UNT and independent school districts like Dallas ISD. We do city projects for City of Dallas, Plano, Allen, Frisco, and Richardson. We also do county projects like Dallas County, Tarrant County, and Hunt County. So most of our work is public sector. So let's talk about the TRE, the Trinity Railway Express project. So this commuter rail was started in December 30 of 1996. It's been about 25 years. And it goes from downtown, from the Union Station. It connects Dallas to Fort Worth. It goes through Irving, Richmond Hills. Fun fact about this commuter rail is that on the first day it started, there were more than 4,000 people who rode this train on the first day. And this is operated by Trinity Metro and DART. So our project is on the Fort Worth side. It's shown in this area, close to I-35W. So the Trinity Railway Express, when it crosses the Trinity River, this is where the project is. The limits are from I-35W on the west side to Sylvania Avenue on the east side. It's a single track section, and it crosses the Trinity River over 764-foot long bridge. And also this is not only used by the Trinity Railway Express, it's used by Amtrak and Union Pacific and BNSF. So it's heavy rail. So the existing bridge condition, this was constructed in 1903. It's more than 100 years old. It requires frequent inspections and maintenance. The freight trains, they have to reduce their speed to 10 miles per hour when they're crossing this bridge. And this causes a lot of delays. They have to wait on the bridge before they proceed to the next junction. So the objective of this project was to rehabilitate the existing bridge. This is considered a historic bridge. It's a truss type of bridge. And then construct a new bridge for a double track next to it. And the bridge foundations, they involve 10-foot diameter offshore monoshafts. And we wanted to have minimal impact on the existing bridge foundation because we were very close to the existing bridge. And of course, we had limited right-of-way. So we had to use retaining walls, and we had also some new embankments. So we had some challenges because of the right-of-way. We have tight space. And we wanted to have no or minimal disruption to the existing track operation during construction. So the field investigation, it involved doing 15 land borings within the limited right-of-way next to existing tracks, and also 2 offshore borings where we used the barge. And this required coordination with the U.S. Army Corps of Engineers, Tarrant Regional Water District, and Trinity Railway Express, and also the other railways that use this alignment. Here are some pictures of the land borings we did. So we tried to stay away from the tracks, 25 feet away. there's a criteria. If you're within 25 feet, it requires flagging, and if a train is coming by, you have to stop the operation, and you may need to move the rig away and come back. So that was a little bit challenging. And we used the barge to drill the offshore borings. So this is the existing bridge, and these are the existing columns. And we wanted to put the new bridge right next to it, so we needed to drill 2 borings close to these columns. We actually had to bring a crane to drop the barge in the river because there was no nearby access. So let's talk about the geotechnical investigation. We'll start with the geologic conditions. So this is the project alignment. It's highlighted in red. And this is the geology map. And keep in mind, the geology map shows you what's at the surface. You know, there's multiple layers on top of each other. But basically, we're seeing here, this is terrace deposits, and this is the terrace deposits, and this is the alluvium. So the project is mostly in the alluvium and terrace deposits. And also in the green, you see the Pow formation, Wiener limestone and dentin clay. It's undivided, so geologically they're considered as the same formation. And on the west side, you see the Fort Worth limestone and Duck Creek formation. And the layers in the DFW area, they dip from the west to the east direction. So for example, the Pow formation would be on top of the Fort Worth limestone. However, because of the river, we have the alluvium deposits and the terrace deposits. So the Fort Worth limestone and Duck Creek formation, it consists mostly of limestone and it has clays in it. The Pow formation, Wiener limestone and dentin clay, undivided also. It consists of alternating layers of limestone, shale, and clay. Then the alluvium deposits and terrace deposits, these are predominantly, they consist of variety of clays, silts, sands, and gravels. And they're typically unconsolidated to semi-consolidated deposits, and they're found near rivers. So this is the boring location plan we had on this project. So we had a bridge crossing at Sylvania Avenue. So we had 2 bridge borings here. And then we had this 760 something foot long bridge crossing the river. So we had 1, 2, 3, we had 5 borings associated with this. 2 of them were in the river. They were water borings. Then we have track also. So these were track borings. Then we had another bridge crossing at the north-south freeway. And also we had another bridge crossing near I-35W. So we collected these borings, and these are the tests we've conducted. So we did moisture content tests. The moisture content is pretty, it's not that costly test, and it gives you an indication about the soil conditions. If they're wet or if they're dry. If they're wet, for example, they could be soft, they could consolidate more. If they're dry, they'll be dense, they'll be stronger, but also they could swell more. So it's a good indication about the soil conditions. Also, we did atomic limits. We use this test for classifying the soils, if they're highly expansive clays or if they're lean clays or not. We also did the number 200 sieve. So this tells us about the material, if it's sandy or if it's clay or silt. We did sieve analysis also to get an idea about the distribution of the granular material. So these 4 tests were mostly for classification. We also did unconfined compression tests, and we did compressive strength on rock, and we did unit dry weight. So these tell us about the strength of the material. We did also direct shear. This test tells us about the long-term strength, which we would need for the global stability of retaining walls. We also did free swell tests and consolidation tests. Those would tell us the potential movement upwards or downwards of the soils. We also did sulfate contents to determine if there are corrosive environments for the concrete. So we would recommend special type of concrete if needed. And also we did total petroleum hydrocarbons to see if there's any contamination along the side. This is an example boring block. I picked B5, it's in the middle of the alignment pretty much, just to give you an idea about typically what we've encountered. There were some fill material. There was sandy lean clay at the top. It was about 6 feet. Then we had fat clays below it with liquid limits above 50. The strength was okay. It was pretty stiff in this area. Then we hit the groundwater around 8 feet and it became soft. Then it was followed by lean clay, then sandy lean clay, then clay sand. And then we had gravels. So this is very typical of alluvium and terrace deposits. It's alternating layers of all kinds of material. And then it was followed by weathered shale, which was followed by limestone, which was followed also by shale. So the geology map shows pretty much what we encountered in our boards. These are TCPs, that's the Texas Comb penetration test. So here we had like 5, this is 11, this is 16. So as we started going deeper, the strength went up a little bit, but then it became soft again until we started hitting the shale. The weathered shale, we had high blow counts. And then in the limestone, we had really good blow counts, you know, like 100 blow counts for almost ½ an inch deflection. Also look at the compressive strength. We had 679 TSF in the limestone. Then we had shale, also it was pretty decent shale. It was about 2 inches deflection for 100 blow counts. And the strength on this boring, for example, was 368 TSF. So this is really the competent material we're looking for foundations. But of course, this is the river, so there's a lot of variability in the river. So we plotted the profile showing the ground surface. So this is the top of the ground. This is where the river is. And also we plotted the depth of rock throughout the alignment. And as you expect, you know, with the river meandering, so this area is all overburdened soils. And then looks like the river reached the limestone on this side and it kind of stopped. It may take several million years for the river, you know, to deteriorate this limestone and move this way, but we won't be around. So talking about the design of foundations. So this project had 4 bridges, as I mentioned earlier, Sylvania Avenue, and then the Trinity River crossing, then this bridge here, and this bridge at I-35W. And we used drill shafts on the project. They ranged anywhere between 24 inches for the smaller bridges, and then 120 inches for the river, the columns in the river. That's like 10-foot diameter, which is huge. So when we design foundations, if we have weak overburdened soils sitting on top of hard rock, we cannot rely on capacity from the overburdened soils because they require large movement to develop the skin friction, which the hard rock will not allow. And I'm going to show you on the next slide. So these are 2 tests we ran on the project actually. So this is a soil compressive strength test. If you look at the strain versus stress, the strain went up roughly, the failure happened around here, which is around 7% strain. So that's what it takes to develop the strength of the soil. While in the rock, it took only almost like 1% strain to develop this high strength. And look at the scale of the strength. Here you're getting like 2 TSF, here you're getting 10 TSF. So the rock is going to be much stronger and it's going to prevent the movement. It would fail if there's no movement. So it will prevent the movement, so the soil will not develop the skin friction. So that's why we ignore it. So to design the capacity of the drill shafts, we used two methods. One of them using the Texas Geotechnical Manual. So this is based on the TCPs, the Texas Cone Penetration Test, which we ran every 5 feet. And we looked only at the rock. So this is for a penetration of this many inches per 100 blows. And you see where it lands on the graph and you find the allowable skin friction. And this includes a factor of safety of 3. So we were mostly, around the 2 to 4 inches deflection, depending whether we're in the limestone or the shale. And this is for the end bearing, same thing. It's based on blows, based on the number of inches per 100 blows. And you read what end bearing. This includes more than 2 as a factor of safety for end bearing. It's a simple method. Basically, you're relying on the Texas Cone Penetration, which is a field test. These are correlations that TxDOT developed over the years. And it's fast, you get results pretty quick because you get the field boring logs and you have the readings already. We also use the FHWA drill shaft manual. So this method is more rigorous. It looks at other parameters. It looks at the rock type, for example. So, for example, limestone is considered as one of the rock types, and shale is considered as a different rock type. There are other types of rocks, but this is what we encountered on this project and mostly what we have in Texas. Also takes into consideration the quality of the rock mass. If you have the joint spacing, if it's more than 10 feet, it's considered excellent. If it's between like 3 to 10 feet, the joint spacing is considered very good. And then if it's slightly weathered, it's good. Then if it's moderately weathered, 1 to 3 feet is considered fair. Then you could have 1 inch to 1 foot, it's poor. And then you can have joints every 2 inch, that would be really very poor. Also, it considers the rock quality designation, RQD. RQD is actually the ratio of the pieces, the core pieces that we get that are more than 4 inches in length, 10 centimeters, divided by the total length of the core run that we do. So typically we do like a 5-foot core run, which would be 60 inches. And then we take this ratio as a percentage. And if you get RQD less than 25%, it's very poor. 25 to 50%, it's poor. Then 51 to 75%, it's fair. 76 to 90% is good, and 91 to 100%, it's excellent. Also, the FHWA method takes into consideration the strength of the concrete, the compressive strength. So that's something we have to consider. What's going to be the specified strength? Typically, it's 4,000 PSI. That's what TxDOT uses, and I believe that's what we use on this project. So after taking all these into consideration, this is what we came up for the unit end bearing. It varied, depending on the location of the columns, if you're close to the river or away from the river. Also, it was dependent on how deep we were. the rock at a shallower depth was weaker than the rock, for example, at a deeper depth. So that's how we came up with the 10 TSF to 16 TSF as end bearing and 2 TSF to 3 TSF as skin friction. Then another challenge we had, whether we need to use permanent casing versus temporary casing. So we are in the alluvium deposits. So we have sands, we have sandy soils, gravels, we have the river, we have high groundwater. So definitely there's a concern of caving in. So we have to use some casing to keep the hole open. Also, the railroads, they have requirements for permanent casings and temporary casings, depending on the location of the shaft and also the location within the shaft. So, for example, this is the track. It will be here. This is about 12 feet from the center line of the track. In this case, for example, they're talking about sheet piles we didn't have on this project. Also H piles we did not have on this project. Then here, if you have, within 25 feet from the track, if you have drill shafts, and if you're within this, what they call zone A, then this requires casing. And it's determined at a slope of 1.5 horizontal to 1 vertical at this distance, which is 7 feet and 9 inches. And then from the edge of the ties at the 1-to-1 slope. Basically, this is the area where we expect the highest stresses, the impacts, from the train, and you want to have casing in this zone. It's required. Then if you're more than 25 feet away, depending on the shaft diameter, if the shaft diameter is less than 30 inches, Note A says you do track monitoring if open hole construction is used. If the diameter is more than 30 inches, then you use temporary casing or slurry displacement method with internal pressure to maintain the concrete inside. So the biggest challenge we had was the offshore drill shafts. Those were really huge 10-foot diameter mono shafts. So we're really relying only on one single shaft at each column. If it fails, it's a disaster. There's no redundancy. And the shafts were installed through the alluvium below the mud line. There's water. So definitely, casing was required, and we had permanent casing requirements for those huge shafts. Concrete curing also near the live tracks was considered. And we required thermal integrity profiling because we wanted to make sure that the shafts, the integrity of the shafts is very important, because if we have any caving in or any impacts, rebar exposure, we could lose the shaft. So this is a plan that shows, this is the existing track in this area. And this is the proposed new track next to it. And this is the existing foundation in this area, and this is the new foundation. And based on the design, we came up with, for those large diameter shafts, this was required to be 61 foot long, and this was 65 feet long. And you can see the water level, so this is underwater. So this is the new shaft location. And one concern we had was, how close are we to the existing foundation? We didn't know what's there because there were no as-builts. Again, this was built in 1903. There was no proper documentation for it. It was based on a spread footing, actually. That was sitting kind of shallow. So we had to do a geophysical study to find the extent of the foundation. So we used electrical resistivity tomography. It's a dipole, inverse Schlumberger geoelectrical arrays. And we used 6 traversing lines perpendicular to the southern edge of the footing. Our objective was really to find what's below the ground, what's the extent of it. We don't want to hit it with a new foundation. So these are the findings of the geophysical study. Basically, this is the depth. This is where the column is. And we were able to determine the extent of the footing below it. So this is what you see above ground. And this is a base sitting there. But below it was this. This is the extent of it. So again, this is what's below the ground, which is forming this shape. And because of our limited right-of-way, we really had to be close. So we were only 4 feet away from that footing that was shown in the geophysical study. And we had to really work with the structural engineer closely, and every foot mattered. We had to negotiate how we can maintain this 4 feet basically. And also, since this is in the river, turbidity fence and oil booms were required to avoid pollutant discharge into the river. Now let's talk about the design of the T-walls. So those are T-shaped precast walls. They're very popular for railroads because their construction is very fast. You just stack them on top of each other, and you use a free draining backfill in between. Quick installation, when you have railroads going, tight schedule, they're very popular for that purpose. So we had 2 retaining walls on the project, and the maximum height was 13 feet. And because we had the limited right-of-way, we had limited construction space also because we have an active track as well. So this is the active track. And the total length of the retaining walls was 1,000 feet combined. When we design retaining walls, we look at these different potential failures. So the first one here is sliding, which basically you would have high lateral pressures that will push the wall outside in a horizontal direction. It just slides. Another stability we look at is overturning. You could have high lateral pressures that could make the wall rotate about this point here, point of fixity. Another item we look at is bearing capacity. You could have failure, it's just that the wall could sink down because the soil is too soft. It can't carry the weight. Don't confuse this with the overturning. Overturning, the wall does not go downwards, it just rotates. This one, it goes down and it tilts. And then we look at the deep-seated stability. This is the global stability, basically. So the whole thing could slide in this shape. So these are the minimum recommended factors of safety. For sliding, we had 1.5. For overturning, it was 2.0. Bearing capacity also 2.0. And global stability 1.5. So we need to be above these factors of safety. So the challenging thing about the T-wall design on this project was that we had 2 tracks. So there's 1 track here, for example, and 1 track there. And the load from the track, depending on its location, it could actually help improve the stability of the wall, or could impact it. It could make it worse. So for example, this track here is applying a vertical pressure on top of the wall. So this vertical force is going to result in higher sliding resistance. Imagine you're trying to pull out something that there's a heavy weight on top of it. You won't be able to pull it out. So this strain is really helping with the sliding. This strain on this side is not. It's actually applying lateral pressures that are pushing the wall, that are exerting the sliding, the forces that will make the wall slide. For bearing capacity, for example, this strain here is applying pressure on the wall directly. This strain also has some effect on the wall, so it's applying bearing pressure. So both are not helping. So you need to consider both of them. For global stability, for example, usually the center is somewhere here, and we have a slip surface in this area. So both of them are applying pressure. That's not helping. We need to consider both strains. Overturning, for example, actually the train load is helping to prevent overturning because it's applying pressure here that's going to prevent the wall from rotating. So it was very critical to figure out, the design. You have to consider the loads with the trains and without the trains, and different combinations, with this train and not this train, or this train and not this train. It was multiple scenarios have to be considered. And to make things complicated, this is, for example, this is the existing track here. And this is the new track next to it. And here's the wall. And the distance from the face of the wall to the track, it actually varied throughout the alignment. So for example, here we had more distance. So that was another factor we have to consider, not only what train load to apply, also where to apply it. So we had to do different cross sections throughout the wall. This was very labor intensive. This is an example of the analysis we did. We used Geo-Studio software. Geo-Studio is one of the most advanced software out there for global stability analysis because it allows you to use the method where you can, basically the analysis is done based on slices. So you take different slices throughout the cross section and you look at the horizontal forces, vertical forces, and the moment at each slice. And then you apply these loads that you have and the weight of the soil. And then at the interface of each slice, the forces have to match. So this software allows us to get the equilibrium to satisfy the horizontal forces, vertical forces, and moment. Not all software can do this. Most of the software available in the market, they satisfy only two of the equilibrium, either horizontal forces and moment, or they don't satisfy all three of them. The answer is not that far off, but this is more accurate, basically. So after we run the global stability, we generate multiple surfaces. You see these dots here. Each dot is an initiation point for a surface. And on this side, you see other dots. These are exit points. So you get multiple surfaces going in between. And then once you find the surface with the lowest factor of safety, we run an optimized surface. So we find actually it's not a circular surface. This is a more critical one that would give even a lower factor of safety. So with this design, our target is to have a more than 1.5 factor of safety. So we got 1.59 with this design. And that's where we adjust, for example, the length of the stems. So we can determine the wall design, basically. And in this case, we had lean clay in this area with sand. It was followed by sand with clay, and then we had limestone below it. The other wall, we had a little bit different conditions. So, we model accurately based on the boring logs that we have. And we use the direct shear strength for long term. Usually the long term is the most critical. We also use the unconfined compressive strength and do U tests for the short term. But long term was more critical in this case, and in most cases. And again, in this case, we considered both train loads because this would result in a lower factor of safety. Another thing we have to consider is eccentricity. So we want to make sure that the resultant force is within the middle third of the wall. So we had to calculate the eccentricity that we're getting, and if it's not within this area, then we could extend the stem longer. So we ensure it's within the middle third. Another item we had to consider is the minimum embedment. You see this mostly on retaining walls. So there are multiple factors that impact the embedment. It could be bearing capacity. You want to achieve, for example, more bearing capacity, you could embed the wall deeper. It could be stability considerations, like the ones I mentioned earlier, for example, sliding. If we're getting a sliding issue, we could also embed the wall deeper, so we have more passive resistance. It could be settlement also, because the wall is it has better material in it, so you're improving the ground below it by embedding it deeper rather than sitting on softer soil at the top. Also, the frost penetration. That's typically the frost penetration in this area is around 1.5 foot, 1 to 1.5 foot. So that's why you see mostly minimum recommendation as 2 feet embedment. Also, there's a shrink swell potential. There's seismic activity, which we don't have much in this area. And also there's scour. If you could have some scour that could erode this area, you want to have more embedment. Another consideration we had for the design for the T walls is the settlement. So we had 2 retaining walls, and we considered the immediate settlement. So this is as you build the embankment or as you're building it, it happens. This is mostly where we have the granular material, so the moisture escapes immediately and you get the immediate settlement. This is like an elastic settlement. We also consider the long-term settlement. So this is if you have clays and it takes a long time for the water to escape from the clays. And also we had to consider, this is without the train load. This is assuming the train is a transient load, so it's not sustained, so it goes by. So we don't consider it. And then we had to consider it with the train load. With the train load, that means, basically the train sits there for a very long time. How likely for that to happen? Probably it's not likely to happen. Is it possible? Yes, it is possible. A train could break down and could sit there for a while. So, so this is what we calculated. This is the immediate settlement for each wall without the train. This is with the train. This is the long-term settlement. And also we looked at the time, how long is it going to take for the settlement to happen? So for example, we had 2.8 inches on retaining wall 2 without the train and 4.36 inches with the train. So we used also an advanced software on this one. We used Settle 3D. It's a very powerful software where it actually models settlement in 3 dimensions. So this is for example, the settlement model. This is without the train. This is the 2.8 inches we got. So this is the embankment you apply on top, and it gives you the settlement. It's mostly in this area, like the middle part of the embankment. And as you go deeper, it diminishes. The effect really, for example, you were getting 0 inches as you go deeper. Oops. So this is also the model with the train load on top. We got 4.36 inches. So this is what went on the plans. Basically, one wall we had 15-foot long stems, and it had the train sitting right on top of it, pretty much. There's no slope here. Also, we used an under drain on this side of the wall at the bottom. And then this is the other wall. We had 17-foot long stem, and we had a slope on top, and the slope varied between like 2:1 to 3:1. But also dependent on the train location. You know, here the train was more on top of the wall. Here the train was further away. So you had two trains that are applying lateral pressures, pushing the wall away. So sliding, for example, was more critical on this wall than this wall. So let's talk about construction of the shafts. I want to talk about the mono shafts that were offshore. Look at the rebar. This is for a 10-foot diameter shaft. It's huge. Actually, the contractor had to build an access pad to this area so they can build the shafts. So these are some pictures of the construction. This is a nice picture showing the existing train. So we were working under conditions where we had a live track next to us. And we actually used thermal integrity profiling. So these yellow cables you see here all around, you can hardly see them on the back also. So they go all around the shaft. These are cables that go down with sensors in them to measure the temperature of the concrete that we use for the thermal integrity profiling. So this is the concern, you know, we didn't want to have shafts looking like this, for example, especially it's a mono shaft. There's no redundancy and a failure would be catastrophic. So this is why we have to test the integrity and make sure the shaft is intact. So we recommended using thermal integrity profiling. The advantages of this method is that it uses temperature versus depth versus quadrant, because we have multiple sensors all around. Also, it tests early after casting, so it speeds the construction, because the way it works, you know, it's detecting the temperature in the concrete. And when the concrete is reacting, when you pour it, you get very high temperatures. So you're getting immediate results. It's telling you where the concrete is as soon as you're pouring it, pretty much. So you get the results usually between 12 to 72 hours, depending on the diameter and the mix design. It evaluates the concrete quality also, and it tells you about the cover and the cage alignment. It avoids false positive issues, and it only reports significant defects. So here's a little bit of theory, which, by the way, this is done by Pile Dynamics Inc. They have a patent, I think, on this technology. And they've shared with me those slides, and I asked permission to use them. So basically, this is the theory of it. You have sensors that are installed all around the diameter of the shaft that go down all the way. In this area at the top, there's convection heat loss to air, or exposure of the shaft. Also, there's some lateral temperature distribution. So if you're monitoring the temperature, you're going to get low temperatures on the top in the sensors here. And then as you start going deeper, you start getting higher temperatures. So this is, for example, the cage diameter. This is the excavation diameter, and the sensors are around the cage. They're tied to the cage, actually. And this is how a temperature distribution would look like, if you take a cross section inside the concrete. So it's pretty high here in this area, and at the edge of the concrete, it starts dropping down. And this is basically, the soil around it. This is the soil temperature. So you have conductive heat loss to soil around the concrete. So this is the kind of shape you get for the temperature distribution. So at the bottom also, there is some loss, some heat loss at the bottom. So you get something like this. So these are actually the actual tests. So this is one of the tests we did on this project. So this is the reinforcement, and these are the sensors around this area. And this is the readings. These are the readings we got. So this is the temperature variation. So as you can see, at the top there is heat loss here because of exposure, and also there's some heat loss at the bottom. But for the most part, you see it's pretty consistent. And also it tells you about the concrete cover. This is what we're mostly interested in. So this is a 10-foot diameter, so it's 60 inches in radius. And you can see the cover, for example, in this area. There's a little bit of overflow, for example. So there's more cover in this area. And then in here you see, this is 60 inches pretty much. So we're getting 60 inches or more throughout. And then, actually here you see the readings from the different sensors. So also it gives you the shape of the shaft. So basically we were getting more than the 10-foot diameter. I mean, yeah, 10-foot shafts. We designed those shafts, getting an extra, bigger diameter that gives us even more capacity in the shafts that we're not even counting on. So the minimum actually it was 10.63 inch cover, and the maximum was 11.95 inches. So we were comfortable that the shafts are built properly. This is actually a picture of the construction of the new bridge. So this is the existing one, and this is the new one right next to it. You can see the existing one is on a huge footing. It's kind of shallow footing, while the new one it's much smaller. We had limited space to build it, but it was relying on a deeper shaft that went all the way into rock, much deeper than this existing footing. Now let's talk about the T-walls. Some of the challenges we had with the T-walls was that there was a heavy rain event when they exposed the subgrade, and water was ponding basically. So these conditions are different than what we designed for. So I went out there and I checked the site, and we had to come up with a quick solution so we don't delay the project. And to make things complicated, we have an existing track right next to it, and we're building one right in this area. So we're only allowed to shut down this track for 12-hour windows. And we were limited for, I don't remember how many days, but it's, I don't know, maybe like 12 days or 20 days throughout the whole project. So we wanted to come with a solution where we can build this fast with minimal impact on the existing track. So we recommended using flex base material and using geogrids on top, so we can bridge over. So we over excavate this soft soil, and we use that material, and then we recommended building the wall halfway, so we gain strength as it consolidates. So, and then after building it halfway, we build the second half and finish the wall with minimal interruption. So we're relying on increased shear strength while using the staged construction. And this is a picture of the wall after it was built. This is the area where we had the soft soils, and this is the other wall also that was built. So with that, I'll open it up for questions.
Thank you, Fadi. Are there any questions? You can type it in the chat if you have a question, and I'm sure appreciate the very informative and clear, straightforward presentation, Fadi. I think it was very good to see
Thank you,
all
Bob.
the analysis you went through.
I have to say this presentation actually came because of you. We published on our website that, you know, about this project. It was a simple project, and then you recommended to ASCE, you know, we do an article on it. So I expanded this. I did an article, and then people liked it and asked me for a presentation. I did a presentation for the Dallas ASCE, and here we are. So thanks to you, Bob, this presentation came along.
Oh, well, I'm glad it did. And we